Hello, everyone. It's really a pleasure to be back. It's been a while, and I had forgotten how nice it is to be in Kiev. So thanks for coming. I really appreciate your interest. And as Igor was saying, I'm an NLP freak. Like I live for this. I breathe NLP, artificial intelligence. I like it. I like to make computers understand how we speak, our ideas, acknowledge representations, all of this. Like, it's my life. I'm really lucky to be doing this for a job. Like, I couldn't be flipping hamburgers or anything like that. So yeah, I'll be talking about recent advances in applied chatbot technology, basically because, this is the short version of a talk that I'll be delivering this weekend, okay, at Kharkiv AI conference, Ukraine. So if any of you happens to go there, you'll be hearing the same stuff, so sorry about that. But anyway, why chatbots? Well, chatbots because maybe you've noticed like there is this rage right now for chatbots, like everybody wants to have a chatbot. We will see later some numbers, it's crazy. So it looked like a very interesting topic. And at the same time, for me, the most important part is that behind the chatbot, there is actually a lot of natural language understanding technology. That is what really makes it cool, right? Like things like, of course, part of speech tagging, chunking, parsing, ontologies, taxonomies, everything. Like, you have to have the right combination of that in order to be able to make something that resembles a viable chatbot, like something that you can actually talk to. So it's very interesting because it's very challenging, but at the same time, you get to touch pretty much every single topic that a person who likes NLP may be interested into. So that's the reason for this talk and for this topic. Having said that, this is basically the very rough idea of the plan. I will give you some overview of what chatbots are, how they're used, nothing that you don't know already probably. Then we will take a good look at the industrial state of the art, because contrary to what most people say, like some people will have you believe that there are already systems that you can talk to normally. That's not even close to true. Then we will see why that's not true, like the current challenges, why most of the systems, you know those apps that you install, you use for a couple of times and you forget that you even installed? Most bots are like that. Like somebody does it, they go live, a handful of users use them, and then nobody remembers about them anymore, right? So why is that? We will see why. And then once we have a good idea of the challenges that we're facing, we will take a look at the recent advances, like how are people dealing with these challenges. And at the end, some conclusions, but probably we will see all of that before getting there anyway. Overview. Can everybody read well the screens and everything? Like, if somebody doesn't see anything or doesn't get something, please let me know. So, user says, "What are you?" And the chatbot will reply something like this, right? So, what you already know is that a chatbot is this interface, usually somewhere like Facebook Messenger, Slack, Skype, whatever, they're all the major platforms. You basically input text, so you write something, and the chatbot replies, at least in some cases. However, there are like a few concepts that get mixed together, right? So there is chatbot 1, right? Chatbot 1 is just a bot, not a chatbot, a bot that lives in a chat. That's the chat part. But it's not something that you chat with. No. It's just a bot, like an automaton, that lives in a chat. So in Slack, you know, like Giphy things and stuff like that, when you ask for a particular Giphy on Slack, that's a bot. Like the system does something for you, like goes to some website, gets a result and serves it to you, but there's no chat, it's just a bot. So first thing. Then we have proper conversational agents. That's when, yes, there is natural language input that you use, and the system usually tries to reply also in natural language output. So basically you are talking for the most part. And in this category, we may have virtual assistant, which is like the general one. And then we have chatbot 2. And that's a chatbot that lives in a chat usually, and that uses natural language input and output. There is usually the assumption that virtual assistants are smarter and have broader AI capabilities than the just standard chatbots. So, okay, that's true. But it's just an assumption. Like, it's not necessarily the case, and sometimes the term chatbot is just being used for pretty much anything, but usually there has to be some natural language input back and forth. That's why I'm interested in the problem. Basically, what I've already said, what you want is to get answers from the system, right? Like usually there is some database, and natural language input provides the best way to just ask for some particular fact, and the system returns that fact to you. Some of the times you want to perform a transaction. In Telefónica, for instance, people usually want to look into their accounts or pay a bill using the chatbot, so that's one use case that we support. And basically, the one thing that all of them fail to do, which for me is the most important one, is what happens when you have partial information, right? Which is basically the, well, depending how, it will be this point, and what that amounts to is, okay, so I know I want something, I don't even know how it's represented in your system, like movies. I want to know what I can do with the chatbot regarding movies. So just say movies. And the system says, sorry, I don't understand. Because it only caught movies, there is nothing else. And yeah, sure, you didn't know what to ask. You just wanted to browse the options. The ideal use case here is that given any small piece of information that you could provide the chatbot should be able to tell you, okay, with this, I can give you these answers. Like this is the more generic answer that I can give you. Like, so if you want movies, do you want to buy a movie? Or do you want to watch a movie? Or do you want information about movies? And that will be the next step. Like no bots right now do that. And it's a pity because basically that's what defines a conversation. Like when you get to the point when the system tries to, get whatever your input is and do something with it and go further, that's what the conversation is, like when you talk to people. That you give some information, they renegotiate the meaning, they add something, then you keep building on top of that. No bot does that. That's the main limitation for conversational intelligence. And this is the number, which is crazy, and people are attributing this to chatbots, actually. Basically, the thing is that in 2008, people were loading 10 apps a month, right? And now the average is 0. Like, you have the apps that you rely on, and that's it. You've forgotten about all the other apps. And people know that, okay, I'm a company, I want to build an app so that people use it. No, nobody's going to use it. Like, they are not installing apps anymore. Most people have WhatsApp or Viber or any of these apps, and what they want is to be able to do things from that app that they already have. They don't want interfaces, they don't want to switch screens, they want the context integrated, and to be able to do anything they can or they want from basically the interfaces they already control, like basically WhatsApp, text messages, and so on. So big number, and as I said, like basically everybody in the industry is considering this to be like the clear sign that, okay, like chatbots are going to be the next big thing, are going to replace apps for the most part, so we have to do something about it. However, and very quickly, chatbots are not even the best interface for most things. Like an app is still the best thing. Like anything that you can do in a few taps is better than just talking to the phone like for 15 seconds to try to get an answer. So it's not obvious exactly what cases the chatbot should actually be used. As a product, it's not easy. However, what is true is that you can't fit anything on the same screen. So there are limitations to what the user interface can do. And at any point, you may be able to ask something. So the thing is, language gives you the broad scope. Like at any point, you can switch context. Whereas with the app, you're always confined to context. That's probably the most interesting use case. In any case, what's really important? Basically what I already just said, people want chatbots to talk like a person. Forget about that, not happening in like 5-10 years. Important as well, the backend should not be a person. Like nowadays, lots of chatbots are actually customer agents disguised as chatbots on the other side, pretending to be bots. That's very sad. It's happening. It should be a crime. That's not a bot, of course. This is what I just said. Ideally, the chatbot will provide a single interface for a number of services. And this is one of the most useful cases. This is why in Telefónica I want to do it, because yes, like, okay, to give you one number, by a wide margin, I think it was like maybe 2 digits percent, like 10-15% of the calls to Telefónica's customer support phone number were to ask for the next Game of Thrones episode. Not even a customer support request. That was the main one. Like 10% of all the calls, that's millions of euros. And of course they were like, okay, like it's always the same sentence. It's like, it always has Game of Thrones. Like just give me the keywords and just send all these people here. That makes sense. And when you have a lot of very specific queries that reoccur all the time, they're very easy to automate, very easy to detect. Okay, that makes sense. That's not even a chatbot anyway. That's just auto replies linked to more refined email filters. But that's what you're doing. You're doing an email filter with an auto reply functionality on top of it. That's not really a chatbot, but that's what you're doing. This makes business sense. Anyway, so just to clarify some ideas here, because there is not going to be any chatbot that makes money anytime soon. And this is the important part, knowledge representation. Basically, we want to avoid this. Like you could have a perfect, not perfect user interface where you can do anything from that would be useless. what you want is some buttons to do the important stuff, and then be able to speak if you need something else, like, okay, I need this. Do you have it? Then bring it to me, if it's not on the screen yet. That's a perfect combination, like some screen and some verbal input. So, bots that I just found today, okay? Kira bot. Kira is a real estate bot that connects you to your dream home. She's always courteous, always learning, blah, blah, blah. Clarison bot lets you stay up to date with your projects without leaving Slack. Well, Slack, okay, I like Slack, so I like this bot. But still, like, who are these guys? Why do they have a chatbot? I mean, does it even make sense for them to have a chatbot? Probably not, but they want one. That's the hype, like everybody wants a chatbot, crazy. Now, this is a real test, just a few days ago. Macy's, okay, like the famous shopping mall in the US. Welcome to Macy's, blah, 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 blah. Start over, happy shopping, whatever. Okay, me. Hi, I'm a man, I'm looking for a leather jacket. I really like leather jackets. Oh, wow, that was the answer. Okay, good. However, I have this problem, like, okay, this is only one, I want to see more. That's a nice one, but what if I want to browse different jackets? Is there any easy way of doing that? You know, random, again, so different jacket, nothing else changes. All right, where can I find a pair of shoes that match this jacket? Guess what? Of course, great intelligence. And finally, pair of shoes. All right, yeah, sure. I mean, but this is keyword search. I mean, that, anyway, ridiculous. Okay, now what's the scary part? You know IBM Watson? I know. That's just sad. Because not even IBM Watson without the right data can do miracles. I mean, that's the thing. So where do you get the data? How do you structure it? How you present it? And how you process it? That's the key part. Not chatbot without data. And definitely, even if you plug IBM Watson in it, nah, not happening. So that's the hype. These are the guys who say that we will be talking to machines soon. But then Andrew Ng, you know Andrew Ng? Yeah? Okay, cool. So basically, he was saying what I was just telling you before, like most of the value of deep learning is for narrow domains, get a lot of data, not mazes. So there are demos, but the conversation always feels awkward in the end because you realize that it's not logically consistent. And basically says companies source conversations to humans, like the human behind the screen that's sad, to get the data and then try to do something with it, but that's about the state of it. So what he says is that basically you should focus, right, exactly, narrow domains, that's the key. Like whenever you have your own database of facts that you can go to basically as your ground truth, that's the questions you need to answer, that's going to be to make a difference. You won't be able to handle open domain question answering, but you have a closed domain, that's the key for it. State of the art. First important point. In terms of metrics, there are no good metrics for assessing this. Like people have been using some of the metrics that people usually use with machine translation, you know, like BLE scores, Meteor, which is a variation of BLE, and things like this. Are you familiar with BLE scores? You are? Everybody? No? Okay. It's very simple. Basically, you have the system generate a candidate translation or a candidate sequence of words that you want to evaluate. And you generate a few things like unigrams, bigrams, you know, unigrams, bigrams, trigrams, all of that. And basically, you have some reference translation or some reference question that a human has given you, ideally more than one. And basically, you see how many of the bigrams and unigrams and so on intersect between the system suggestion and the human suggestion. So it's a very simple process, actually. These are more refined. This one uses like wordnet synonyms. Some other metrics, like not only bigrams, but some more interesting features. But basically, the idea is always the same. Now look at the numbers. Like this is the correlation between the system suggestions and the human agreement, right? So when humans consider that the system's answer does make sense or not, if you ask two humans, they agree 90% of the time. Whereas if you use these metrics to rank, okay, this answer is actually a good answer given this expectation, they tell you one thing or the other, but that's only correct, like, I mean, that only correlates with human judgments this much. So it's like we are 8 times lower in terms of correlation as humans would normally agree, right? So we have no way of scoring that because you are not going to take an army of human evaluators and have them read output from the system, like never edited output, to extract correlations. So that's a big problem because without good metrics, there is no way we can improve technology. So that's a big pending issue right there. That number is like 90 compared to 20, or that's terrible metrics anyway. So big problem that we don't know whether we are improving or not. The other thing is these guys, Intento, machine learning providers, cloud providers, did a benchmark of different systems like IBM, as we saw before, plus Microsoft's and a few others. And they did the usual task. In the usual task, you have annotated data where you have intents, okay, such as get weather, like what's the weather like? Or is it going to rain tomorrow? Things like this. And you have a bunch of sentences annotated, mapped to that intent, and basically you train the system to predict new cases, right? So they gather this data, they perform a threefold 80-20 cross-validation using the different providers. The rest is not important right here, and these were the numbers. Like, based on this great performance, again, remember what we saw about IBM Watson, okay? That's their 99, okay? So be careful here. Basically what this means is that if you train the system with enough data, the system is going to be able to recognize new cases of the same data. Sure, why not? Particularly if you're working in a narrow domain. But what will happen if you took that system in an open domain, right? Like, that's basically this other column. They were making all the false positives they could, like, namely, whenever you were asking for some of the domains that were not in the training data set, okay? Like, you had get weather, get movie, a few more. Okay, I'm going to ask something unrelated, okay? Like, I'm going to ask, what is the capital of Ukraine? IBM would always give you get weather or one of the ones I knew. Like, it will never tell you this is, I know that I don't know the answer to this. Like, it can't tell. You can build it into it, but still, it makes you realize how stupid the system is because it's actually not using a representation of what you're asking. It's just, pattern matching, like always. And the same is true for Microsoft, actually, same problem. These guys, Amazon not clear because you couldn't upload the data, so the benchmark is not clear there, but definitely still struggling. And just a few guys like API for Google and Snips take this seriously, try to do something about it. But anyway, big limitation that the system is actually not aware of what it doesn't know, because that's key. Like, in order to be able to continue a conversation or not, you need to know whether the input is something that you should be able to answer or not. So, yeah, important stuff. The rest of the parameters are not really important, but the key message here is that actually these are the same numbers we're getting in Telefónica with our data. Is also like 99, 98, like something huge like that. First problem is when you take that and use it on real utterances from users, it usually drops 10% like off the bat, like that, easily. And usually this means overfitting, right? Basically because at least these guys, probably most others, they're using logistic regression, which tends to overfit, so that's also a big part of it. We're still having problems with that. But anyway, this is the state of the art. So basically what this tells you is that most big providers, for the huge craze trend of chatbots, are just training a classifier, standard classifier, logistic regression, whatever, nothing too fancy, over a few thousand examples, and that's it. And then they put that in the market, and that's what you use for, like all these movie-like scenarios. It's crazy. So anyway, that's the market. Okay, this is important, but I don't know if I have time. Okay. Well, you should see the rest of the talk. It's like, so anyway, this is the thing. Like, you can see the performance at 96, 90, almost 97, or 97 actually, is reached with 100 examples. And then each new point is extremely painful. It's a logarithmic scale, so it takes half as much data as here to raise a bit, and then more than twice as much to get a bit farther, and then it's like 10 times to, just move the needle a little bit. So what it's telling you is that these systems, for whatever the use case, with, some data, but not crazy data, you are already going to be doing almost as good as you can reasonably expect. And after that, like, wow, if people really use your chatbot, you may be able to collect more and more training instances so you can expand that curve. But it probably doesn't make sense after this point. So there is a big question of, okay, how much well, I mean, you know the data. Like, I don't need a lot of data to be able to train a system that can answer reasonably well. So where do I get that data from? That's one of the things that I'm hoping we'll be able to say today, because that's basically it. Like, if you can train a lot of different intents with little data really fast, that's what's going to give you the best performance, because you can take this, which is, you know, the reasonable performance you can expect, and use it in many different cases, many different chatbots, many different industries, many different use cases for the same industry. So I think that's the key issue here. But anyway, very interesting benchmark by these guys. Current challenges. Okay, let's be real, okay? No, if you realize my previous messages were well written, so no, not happening. I'm a guy looking for leather jackets, okay? So no leather, no, nothing like that, leather. And of course, well, let's keep it like that for now. And then what can I find? There's the conversation continues, yeah. Of course, first problem, as you know, lexical variance, right? Like in language, we have lots of different examples. Just to give you, I mean, this is something that we struggle with in Telefónica. So I have a problem with my cable, like I need to fix my internet connection or whatever. This can translate into all of these different ways of expressing this intent, so good luck finding all the sentences. And of course, each of these can then be expanded by the standard linguistic variation, like apostrophes, different words, synonyms, all of that. I can say we've been, okay, of course, yeah, this can be normalized with expressions, same for this for the most part. We've been doing this in Telefónica because it's very easy and you can be very practical. So actually I was surprised to see that in a week, 1 week project, no more than that, basically building a regular expression filter with some intelligence but nothing fancy, like even stupider than IBM, we were able to go from 89 F1 score to 95, so 6 points like that with a 5% positive rate. That means that this was the improvement just by hitting 5% of all sentences. For 95%, we didn't even find anything. But for those that we found something, like that 5%, that alone allowed us to improve this much. So it was clearly some really bad cases that were causing a lot of problems. If we just a simple filter like this, we were able to really bump up the performance. This was the task where we measured these results, but it was very interesting because, yeah, this is a problem, but it can be handled reasonably well, so not that much of a problem. This is much more interesting, but we will see later why. Basically, variation inside intent, right? Because you have the same intent, like technical problem, let's call it, but what actually will determine the final intent is this entity. Like, if your problem is with internet connection, you will send the user somewhere. Whereas if the problem is with the SIM, you will probably give a different answer. So if you are detecting the intent, like something does not work, the intent alone is not enough. You need to know the specific entity to be able to send the guy to the right answer. And we will see why that's a problem. Just keep that in mind for now. Yeah, I'm going because it's already 7:30, so I have to rush. But I think I have a good example of this later on. Yeah, okay, let's skip quickly to this part. So basically, this is the problem. Imagine this is our training data set, okay? So those sentences about the intents that we upload to Microsoft and so on. And basically, this is what we observe, like buy a red jacket, find a jacket with straps for blah, 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 blah. And now imagine that at runtime, what we get is, where can I buy for my friend? Okay, yeah, buy. I observe buy. I know buy goes before this entity. I also have for behind the entity in another example, so that's reasonable. I know the entity is going to start after buy and it's going to end before for. So that's fine, I have that entity, good. What about this one? Of course, we don't have need in our, toy example, but bear with me. Need didn't appear in our data set. That, as the end of the entity, didn't either. So now the system is going to take the whole thing as the entity. At least that's going to be, the hypothesis. And of course, we get a segmentation issue. Wait a sec. Oh, right. Basically, we can have different entities with the same distribution, which means that if you always have the intent via something and via something, and if you wanted to have two entities for that intent, like in case, okay, if somebody tells me for the intent to buy, I want to buy something, And then I say, I know they want to buy something, so I'm going to make a decision based on the entity. If they want to buy a leather jacket, I'll send them one way. And if they want to buy a wallet, I'll send them to a different page. Well, you can't do that in the current framework, because in the current framework, the intent is going to be one, and the contexts are going to be the same. So even if you implement two entities, let's say jacket and wallet, they're going to appear after by both of them. And because the entity prediction works by the preceding context, the system is going to be ambiguous. Like, it will never be able to choose between one or the other, because they always appear both in the same context. Like, you buy something, you buy something. So the system won't be able to detect one entity or the other. And you will never be able to send the user to one place or the other. And this is happening when, like, not all the APIs out there in the market don't make this distinction, because obviously dealing with these will require internal dictionaries, like, really knowing your database, being able to map it to actual items in your database and so on. And that's too complicated, so basically nobody's offering that. This is a big opportunity for improvement, because of course, there are some startups who are already going beyond this, but not that many. So it's something to keep in mind, because most technologies that are currently available won't be able to handle this. Okay, another problem, but if I don't speed up, I won't be able to get to the solutions. So I'm going to skip this. This is basically what I just described. Like, when we keep, like, if we know this entity, but somebody enters this one, we won't be able to find a match, right? That kind of thing. And okay, and the most interesting part, let's say, what happens, and this is what it gets like really, really tough. What happens if the user says something like, hey, with a lot of conditions, let's say, I need to buy a men's red leather jacket with straps for my friend, okay? Like, pretty complex query. But we say, okay, in the end, this is just all features of the same object. So if I just do an intersection and try to find an item that has all these features, that's going to be it. And if there is no item, that's it. Sure, let's try that. So I'll skip the formalization. This is trivial. Basically, one is a filter that takes the original document space. It keeps slashing by each word until it finds the last result, right? Right. But what happens, let's imagine that we don't have the perfect match. We don't have the 5 out of 5 match, but we have 4 3 out of 5 matches, right? And these are actually results from Alibaba. Like, they have all of this. So you can actually Google for this and you'll get the results. So you can have leather straps, men, sure, yeah, for watches. You can have red leather men's shoes, of course, yeah, and so on, right? Like, there are all the different 3 out of 5 combinations have results, and they are there. So the question is, okay, we have something, but we can't go to the user and give this and, like, look, I'm smart. I found 4 things unrelated, or more or less, deal with it. No, that's not a conversational bot, or it shouldn't be. So the question is, how can we really improve this, and how can we rank these results better? Well, the obvious way of doing it is fixing that problem. The problem is the filter. Of course, we're using a very naive filter. Just takes one word, a collection of documents, and keeps filtering documents by that word, right? Like, we can do better. So we have to fix that part. And we could simply do this. Like, we add a parameter to the filter, which is the relation in which the word stands in the query, right? We will see an example. But basically, that's going to allow us to say, okay, when I have this word, if that word is in a different dependency relation than the other, or it's closer to it, give it a lower weight or a higher weight, depending on how close it is, so that the right results move up and the bad results go down. To do that, because this metric will be based on dependencies, we will need a dependency parse. Nowadays, we can get that from Stanford. Of course, Stanford is not perfect either. It's a very famous parser, usually used, most pipelines, is actually really good. But of course, in a narrow domain, it makes mistakes. Like, there are some things that depend on the domain. So as you can see, the red parts here are errors in the parse. Like, basically, when I ask, I need to buy a man's red leather jacket, blah, 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 he actually thought that goes with men's. So basically, I actually don't know what he's trying to see, because this is what he's trying to say, because this is plural. So A should never be a part of this. But anyway, like, he understood, like, it's a men's jacket, you know, like, or something like that. Again, doesn't make sense, because it's singular and this is plural, but anyway, some error there. I don't know which one. And then it understood that the straps were for my friend, not for the jacket. So like, you know, somewhere there is your friend like this strap that he can move or something like that. Of course, we don't want that. This is the right parse. And in any case, basically what we're going to do is we're going to take the previous list of results. We're going to see, okay, so let's say jacket. Jacket is right below by, like it's the head of the phrase that goes after by. So basically, jacket's distance with respect to by is one dependency, okay? What about leather? Well, leather hangs from jacket, it's modifying jacket. So it's going to be 1 and 2 for leather, okay? So distance 2. And for red, since it modifies leather, it could modify jacket. Let's assume it modifies leather, it's going to be 3, okay? So now we know, okay, if I get a match for jacket, because my jacket is closer to the dependency that I'm trying to resolve, I'm going to give it a higher score. If I get a match for leather, it's going to be somewhere in between. And if it's a match for red, I'm going to push it a bit further, right? Basically, that's what we do here. We tell the system, okay, assign to each result a weight which is the inverse of the distance from the dependency that I'm currently evaluating. And this is it, basically. Well, I'll jump to the final results. You'll have to trust me on the math, but it's not very complex math. But basically, this is what happens. If your input is red leather jacket, so let's assume that let's say the head is jacket, so I'm actually looking for a jacket. And the system doesn't have an exact red leather jacket, but it has a black leather jacket and it has a red leather wallet. Because jacket is the closest word to my dependency, okay? Like the first term that I was analyzing, the weight for this is going to be 1 of the bad. So this is the one we see here. Whereas wallet is missing that 1, it's lower because the first dependency was for wallet, and wallet was not in my query. Remember, the query was red leather jacket. So that's the thing. Like, if the word is not there, we miss the weight for the first, the highest weight word, so that already drops it down. Whereas here, there is, the word that we're looking for is there as the head, so we assign the full score, and that's how we can weight the results for this query higher than those. Okay? Everybody follow? Yeah? Simple? Okay. So basically that's a way. Like you implement this into your ranking result algorithm, and you can basically come up with a much more plausible list of results. Why is this important? Basically because, as we were saying before, in a conversation, you will have to be negotiating hypotheses all the time. Like you will have many results that match. You will need to rank them on real time, and you will need to ask the user for confirmation on some. Like you will want to offer the user some options, and you want the user to accept some of those to be able to continue the conversation. And basically this tells you the system is really understanding something out of nothing. Like at least it can tell the jacket and wallet are the important words here. And then it's worse a result that doesn't have jacket and that it has wallet than a result that is a leather jacket, which is just a different color. So higher score, lower score. Okay. And well, as I was saying, Stanford parsers are not always perfect. And actually in recent research, these guys proved that with unstructured input, so basically what you would get in chatbots, standard parser performance drops to 80%. It's usually 93%, or some cases 96, 97. And with this input, it's 80%. That's already pretty bad. I mean, it's doable. You can still do things with that, but it's like 18 or 15% lower than you would normally expect. So it's a big issue, and you need to be able, like, even Stanford, in order to do the parse, needs the kind of information that you will need to rank the list of results, right? So where do we get that information from? We'll get there, I'm hoping. I may need to speed a bit more, but I think we'll make it. Oh, well, we have a questions and answers time, right? We started a bit late, so when is that? Okay. I'll try. So anyway, Stanford, how to build a tree. Like we know we want some of the parsers, but some of the parsers are going to be incorrect. How do we find the right attachment for those parsers? How do we know exactly how to split the tree? This is the way. Like basically, this could be true, this could be true, this is true, but this is scary. Like this is like, no, we don't want that. But it can happen. We can think of a context where that beds leather jacket. That's technically what that is. So anyway, how do we discriminate this, right? How we make these differences? blah, blah, blah. So as I was saying, we use the tree, the parse tree, and so on. And basically, in the end, what we need is just a function that gives us a higher probability for the attachment of men's to jacket than the attachment of men's to leather, because actually we should have not observed any results for this, so the probability here should be 0.00 something, but it should be way lower anyway. Whereas in this case, it should be more or less the same, like red can modify leather, sure, red leather, why not? Red can modify jacket, absolutely. So more or less equally probable, and this is the only one that fails, right? And this way we can discriminate the analysis, because they're structurally the same, right? So where do we get this information? That's a lot of information, actually, right? Like, okay, where can we get all these dependencies from so we can start making these decisions in runtime while building the tree and so on for every single word? Really, that's a lot of information. Where does it come from? It's tough to get. There are some companies who are building their own pipelines for extracting information. Basically, they go through millions and millions of pages, blogs, whatever they can find, and they parse them and they extract these kind of probabilities, like how often leather modifies jacket, how often men's goes with jacket, and so on. So it's definitely out there. People are doing it. It's a way, and you can build a pretty huge database with that, and you can then feed it into the system. Google is actually doing that with semantic parsing, and they've been doing it already for a few years, so they're working on this. At a lower level, we can approximate it rather than going to the word level, trying to abstract and go into, this is called, it has different names, but the name that I like because of the hype is super senses, okay, like abstract senses. Basically, you're going beyond the token level, and instead of using men's or women's or whatever, you work at the person level, right? Because it's not always going to work, but it's going to allow you to make inference. Like here, even if you don't have enough evidence to really pinpoint if men's goes with jacket, you can, maybe you didn't acquire that. But through some other examples, you did observe that in some other cases, person words were not associated with materials, whereas person words were associated with clothing items, like children, trousers, women's, blouse, and so on, right? So basically, you can, on all the data you can acquire these relationships, you can model them as the level which is more abstract, so it gives you more data, and you can use these to make the decisions rather than working at the word level. Because yes, word level is too specific. You probably will never have enough data unless you have this whole pipeline to extract it from many different sources. So basically, this would allow you to handle most cases, really problematic cases, with much less data and in a way that should be able to handle this problem. This is actually what we're doing at Telefónica. We still don't have the whole workflow in place, but this is what we're working on right now. I think this is basically what I just said. Okay, right, and this all was just for the first part of the conversation that I was having with the chatbot. So definitely lots of work to be done here. Anyway, and right, this is too complicated for now, so I'm going to skip it. But basically, it's just the question of, okay, so in the conversation, if I say, that's a nice one, but I want to see different jackets, the system at some point needs to be able to understand that one here refers to jacket, and that refers to the last result that that the system just computed, and this kind of thing, right? It's still too complicated. It's basically coreference resolution. So let's just say that if you have enough knowledge to do what we just described, like resolve the parse tree and runtime and be able to make those decisions regarding the attachment, you should already have all the information you need to kind of approximate this. It's not obvious, but you should. However, the key part here and where it really, really affects the conversation is the case where somebody probably gave you some information. Let's say you the chatbot asked for the bank account number or for a phone number, and you gave a number, and you keep going in the conversation, then you realize that the number is incorrect, and you want to change it, and you tell the chatbot, I want to change the number, and the chatbot's like, I don't understand. I want to change the number. It's like, I can't support change number, that kind of thing. Very frustrating, because basically it has no idea of the information it's using, right? So that's pretty much this problem. Okay, so while you're following the conversation, if at any point there is an attachment and you need to go back, like you were following down some branch and suddenly you want to go some previous branch, does the system know how to get there? Like, is it aware of the stage that it's gone through so that it can go back? Usually not. But some people, that's the last part of the talk, are working on this. So keep it in mind as a problem. We'll get back to the solution later. Blah, blah, blah. Blah, 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 blah. These are the examples. So forget the last thing I said, go back, all of this, right? Third option in the menu, many different, this is conversational, so it's not happening. Okay, and this is also interesting, but it's the same thing. So basically, very quickly, when the same utterance combines different intents, right? Like basically, in this case, you would like the system to recognize that here the user is evaluating the item, like a nice jacket, good jacket, so you update the preferences. Whereas here he asks to browse the catalog, so more items. And here he asks for information. So it's actually 3 different intents in one, right? Again, if you have enough information to resolve each of these perfectly, you will have enough information to recognize all of them in the same utterance. But it's a whole different problem. We don't have a lot of time, so just scary, but that's it. Yeah, I would like to cover this part. Yeah, anyway. So come to Kharkiv and you'll see the rest. Okay. Blah, blah, blah. I just want to jump to the solutions at this point. Otherwise, you will feel that it's very difficult to make a chatbot and there is no hope. And I don't want that to be the case. So, okay. Okay, these are all the things that we should be doing to get to a proper, decent chatbot. And forget about the previous ones. This is where it gets really important. This is what we just discussed, like how do we resolve attachments, how do we build the trees in a way that we can filter the results to come up with the perfect list of suggestions for the user, right? That's what we're going to do. Yeah, summary. Okay, so very quick. So self-presence inference. This is what I was telling you before, like we need to abstract from word token level to higher than that so that we can reason and we can perform inference in runtime, right? And that's this research, these guys were doing that. Basically, this is the taxonomy they're considering, okay? And their goal is to label any instances of these entities, try to predict their categories, right? Like very simple. But very useful because, again, you will be able to create a representation of artist for all the instances of any actor, any director, any author, and so on, which would make it very reliable when detecting artists, right? And the same for every other category, same for location, organization, and so on, which gives you a very robust, very high coverage entity detection step, right? And this is very important because those entities are going to be the foundation of everything else. All the decisions that you're going to be making later when building the parse tree are going to be conditioned on these entities because they're going to be basically how strongly does this entity associate with this other entity. So the better your representation of the entities is and the more information you've been able to map to that taxonomy, the better the decisions you make are going to be when building the trees, right? So very important. This is, well, yeah, the guys actually, the authors were using 2 different taxonomies. The results vary, yeah, a bit, but anyway. And the workflow is very simple, actually. Like they take Freebase, they take the categories in Freebase and they map them to categories in these taxonomies, okay? And basically they take some huge collection of documents in this case, well, not that huge, but big enough, 133,000 news documents, okay? And they go through all those documents, they search for mentions of the entities in Freebase, and whenever they see one of those mentions, they query Freebase, okay, what relations do you have for this entity? Okay, and what categories and taxonomy do I have for this entity? And basically they update the vector for that node in the taxonomy so that after that they can use the information for prediction, right? And for prediction they actually use, I know it's a classifier, I don't remember which one, but I guess any would be fine. They are comparing, right, these are conditional random fields, if I'm correct, so logistic regression applied to sequence problems, right? So I'm pretty sure it's also logistic regression here. These are the features they use, so standard features, well, not so standard, actually this is pretty advanced, like the dependency role, not everybody uses that, clusters and so on. Yeah, actually that's a lot of features on top of the taxonomy. But anyway, so they train a classifier with that information, right? Like they build the vectors for each entity type they want to detect, and then when they predict, they ask the system, okay, given this new word that I don't know, is this an artist? Is this a place? What is this? We're able to get to 73% F1, which is not bad for a task this complex. Like, remember that in this case, you have to scan all the tokens in a sentence, meaning you have to go for every single word, all of them. So the chances for making mistakes are huge, because it's not just like, okay, I have a few candidates, I need to make a decision what's the best candidate. Yeah, that's one thing. But when you have a whole sentence with all the pronouns, all the verbs, all the determiners, everything there, and you have to go through each one and make a prediction and say, okay, yeah, this is a place, or this is a person, or this is not a person, and so on. Even in negative case, like no person, no anything, no anything, no anything for everyone, there is a lot of chances of making mistakes. So in this case, precision 80 is actually pretty good, and an overall F score of 1 is actually very reasonable. And what this is telling us is that this is a reasonable way to expand the coverage and be able to map that. Basically, any sentence with any tokens to a more abstract representation for which you can learn the semantic knowledge that you need to later make decisions in order to split the trees, right? So interesting, I think. I really like this topic. I think it's very powerful in order to make these inferences happen and be able to make those decisions. So important. Now, let me see how much time, because it's going to be tough. Okay, Igor? No, Igor. Igor, how much time? Yeah, I know.
I think we should
wrap it up.
Wrap it up and have a Q&A session.
Okay, let me see what I can do here very quickly. Yeah, because this is cool. Okay, yes, very quickly. Going back to the point of having the structure knowledge base. Okay, like actually going back to the previous point of, to make this possible, we're going to work on a closed domain. Okay, like no open domain question answering. Yes, let's focus on a domain. These guys focus on Olympic Games. Okay. And they implemented a fully neuralized pipeline, which basically means answering questions from this database will normally require SQL queries, right? Like select these many rows from this table, where in this condition, and so on, right? So basically, select city where year equals 2012, and you get the Olympic Games, London. Okay, that was a city, and so on, right? You will use SQL. These guys use a neural network, forgot about SQL, just jumped straight in, built word embedding representations for each column, trained over a few examples, and basically the system learned the logic as to when to apply. Like if you ask for longest, the system learned to associate longest with the max function, right? And when given the vector, like a word like city, the system learned that, okay, every time I have the word city in the input, I see that this table has a bigger weight in my results. So basically, I'm going to learn that the word city correlates with this particular table, right? And everything like that for like basically the generated training data, but we're just talking 20, like these, like the results that we're giving, yeah, too much. Anyway, so these are the results, okay? This is their approach. This is their approach with biases. So let's forget about this one. This is the precision, if I remember correctly, that they achieve. And this is how much data you used, okay? So 25,000 sentences. But remember the previous benchmark. Like with industrial systems, okay, the people from Intento, they were basically feeding 17,000. So not that far away, right? 17,000 to train the intents, but the system was not really learning the logic. Here, with more or less the same data, it's actually learning compositionally how to derive, basically it's building the tree, because even if you ask for a complex query, like let's say, what is the city with the longest games in days after 2012? The system will compute each of those separately, like it will go column by column, embeddings by embeddings, calculating every step, and will do that with you without you telling it, right? And compositionally, which means that any new combination of the same functions will be handled. So it's not like you have to teach out examples and the system will learn by association. It's just that it learns the logic in a modular way, and then any other combination of the same logic, no matter how long, no matter how different, no matter whether you update the table, it's always updated. Like you always get results dynamically. That's why it's so cool, because this is basically unsupervised question answering. You have to train it, but with enough data that you usually have in a database in a closed domain, you actually can generate that data. The system will learn how to query the data for you, and it's going to be able to answer new questions from scratch. So this is actually one of the coolest research I've come across recently. It's still experimental, but last thing, this Sempre, actually, it's, this. It's a toolkit for training semantic parsers, blah, blah, blah. It's rule-based, and it's actually really good. Like, it uses internal logical representations and everything, so it's the whole deal. But as you can see, it doesn't perform nearly as well for some of the use cases, even though this one has no internal logic, no knowledge of anything, just a neural network trained on data. So it's really cool stuff. I definitely, if you like this topic, I definitely recommend to go back to this paper because it's pretty cool. And basically, if you have this, like if you have a system that can take a table and can basically estimate all the right weights, like for a word like city, it can find what is the right column that it needs to go to and that it needs to take the value year and all of this. Basically, you can solve cases like men's leather and all of that. Like the ones basically you know where to split the tree at every single point based on your data.
Thank Jordi for his presentation.